gonna get the recording to the cloud going. And pull up the chat. Chat go. And what I'm going to do is share a file with you that'll help you with this section. Maybe I can find it. Where... Oh, created these last night. See, did you get the file? There we go, in the chat.
Perfect.
All right, excellent. All right, so the finance mathematics. Obviously, it's going to be important if you do anything like buying a car or getting a loan for a house or just saving for retirement, etc. So we're trying to get students to have some formulas and some experience with using the formulas. These formulas that I'll give you in these notes will be the ones that you have on the exam as well. So you will have these formulas, you just need to know how to use them. They might not be labeled, but they'll still have the formula. So you just look at them, recognize them, etc. So the first thing that we need to discuss is, let me just go full screen, make this a little bigger. There we go. Lump sum versus periodic. So there are basically three formulas. Two of them are very similar. They do not look nice, but they're not bad to work with. And there's two situations that we'll find ourselves in. One is lump sums, and the others are for periodic payments, deposits, or withdrawals. So a lump sum is an investment or a deposit that you make once at the beginning of the investment. You don't make any other further deposits or withdrawals from the account during the investment. So this often happens when people get like a payoff from a lawsuit or with an inheritance perhaps, or winning the lottery or a tax return. All of a sudden you have just a lump sum of money and you want to put it in the bank. Now the other type is periodic. So this type of investment or loan has you make a payment, deposit, or withdraw at a consistent frequency, whether it's monthly or yearly or daily. So for example, credit card companies will compute your interest on a daily basis. So you usually see the word each or every in the problem. So for lump sum problems, there's basically two types of interest that might be used. One is simple interest and the other is compound interest. Compound interest will also be the main type of interest used in the periodic problems. So first off, simple interest. So simple interest is actually the interest that, like a credit card that computes interest on a daily basis. Once a day, they'll run this little formula and then find that value and then add that to your account, how much you owe for a credit card, or if it's a savings, how much they're going to give you in interest at the end of the day. In order to understand these formulas, let's introduce a couple of things. First is the principal. The P is the amount of money your account begins with. It's the initial one-time investment or deposit. The rate R is the annual growth rate, often referred to as APR, annual percent rate. It's usually given as a percentage, and it must be converted to decimal form before being used in formulas. So for example, 6.35%, you would work with R equals 0.0635. as far as converting from the percent to decimal, the easiest thing to do is just divide by 0. Sorry, divide by 0. That's not a good thing, is it? Divide by 100. So 6.35 divided by 100. Now, a lot of students do the move the decimal place twice, but then when there's like 0.8%, then students, don't move it twice for whatever reason. So it's the safest just to divide by 100. And the time is the amount the investment lasts. It's measured in years. So 18 months, you would have to convert that by 18 months, divided by 12 months a year, into 1.5. So as an example, you deposit 400 in an account earning 4.2% simple interest. How much will you have in the account in 10 years? The formula is I equals PRT. Surprised I didn't put that in a box somewhere. I'll probably fix that. I equals PRT. I stands for interest. And we know what PR and T are. So the deposit 400 in an account, it doesn't say 400 each month or 400 each year or anything 400 every 2 weeks or something like that. So that's how we can tell this is not a periodic one. This is a lump sum, one-time investment. Okay, so we have P equals 400. R, we convert the 4.2% to 0.042. And T is 10 years, so T equals 10. We plug it into the formula, calculator, we make $168. If we wanted to find out how much money is in the account after 10 years, then we could work out the final amount, A equals P plus I. Just add the interest back to the original amount. And that's how much you would have. Now, you don't necessarily have that in the account. Simple interest is typically done by you get a check in the mail for the interest payment. So an example of simple interest would be like the dividends you might get from stocks. The money you've earned, they just send it to you. You don't necessarily have enough money to go around and turn in and buy another stock. So they can't necessarily put that money that you've earned back into the account. So they just send you a dividend check. And of course, we'd want to make sure that we are doing proper units for these story problems like dollar signs. So I don't know how much time we'll have for all the you try it's in the notes. So I will reserve these for the harder problems. It's pretty simple. It'll be 650 times 0.054 times 15.
Perfect.
Yep. Now, compound interest, widespread in finance. Compounding is when the interest is computed and the earned interest is added back into the account. So the effect of the compounding is to increase the amount in the account for the next interest computation. So it accelerates the earning of interest or accelerates the payment you need to on the interest if it's a loan. In order to apply the compound interest formula, we need one additional definition. It's N. Lowercase n is the number of compounding periods in 1 year. So this is table is for the common compounding type. So in the problem, it will state like compounded quarterly. So this is what you need to look for in the problem to know that it's a compounding problem. And therefore, we use this compound interest formula. And then compounded quarterly, we know that quarterly, there's 4 quarters in a year. So the interest would be created 4 times. So n equals 4 for this problem. So what do you think for number 2 on the right, the you try? So here's the word compounded monthly. What would you use for n?
The 12.
Yep. So we get n equals 12. And then we know what formula to use because it says compounded monthly. So this is the compounding. called the periodic compounding interest formula. But so to use this, we need to determine P. This should be a lump sum problem. So we deposit 6,000 into an account. It doesn't say each month or each year, etc. So it's just deposit 6,000 into an account, lump sum. So we have P equals 6,000. R, we convert the interest rate into a decimal. T is 5 years. And we've already seen that N equals 4 for compounding quarterly. So we plug these into the simple, oh my goodness. So I am seeing some mistakes in my notes. I will work these before my next time I use them. That's great. So plugging these into the compound interest formula, we have A equals, there's our formula, 6,000 for P, 0.0385 for R, 4 for N, and the exponent 4 for N and 5 for T. Now, the common mistake students make is rounding in these problems. So if at all possible, you want to put the entire piece, this whole thing into the calculator at once, if possible. And this one, these definitely are. So in order to do this, you really want to read from left to right. So 6,000, then there's a left parenthesis, then 1 plus 0.0385, and then divide by 4. Now a right parenthesis. And now we have an exponent. So this is my exponent button. Exponent. And now in here, I also have parentheses. Parenthesis 4 and times 5. So by using all the original data, the calculator is going to compute this all at once and jump straight to the final answer. If you don't do it this way, then you need to make sure that you write every digit that the calculator gives you and use that every step, which is fine. It's just more writing and more typing with your fingers. Eventually, we get the number, and then in this problem, it says round to the nearest cent. So we go to 0.966 to 0.97.
Okay.
Now I want to point out why. So let me remove the parentheses around the exponent. These parentheses. Now it's wrong.
Okay.
Now the formula is given. I wonder if I can find them real quick. Look for a moment. The formula is given. Do not have on those parentheses. So it becomes important for you to make sure you use the parentheses. And so I just like to write them at each time. Oops. Yeah, so I've added the parentheses. Hopefully the formulas on the exam have those parentheses now. I think they're important because if you don't use them, you get the answer wrong.
Mm-hmm.
Now, if you're doing this by hand, then you can do the 4 times 5 is 20. And now those parentheses won't be necessary because there's no operation involved in that exponent. So a couple of pointers, again, the set of parentheses around the exponent. Also the amount of precision used at each line, no rounding. And it's easy to do if you type the whole thing into your calculator at once. I think the calculator is probably what makes this homework set the hardest.
Mm-hmm.
Yep. So any questions with the compound interest? Finding the N values? Yeah.
Will the N values
table?
be on the test or no?
No. Nope.
Perfect. That is the only thing I think.
Yep. Those you'll have to basically memorize or understand.
Okay. And then on the problem that we just did,
Yes,
if we do the 4 times 5, just like simplify that before we do the whole problem, that's fine.
yes. So if this whole thing had just been 20, now you're back to getting the correct answer.
Okay.
Yep.
Yep, I think I'm good on that.
Great. There's a third type of compounding, not a third, another type of compounding called continuous compounding. And it's a different formula altogether. And it's not covered in this module, even though we've seen the formula with the exponential growth module. Okay, so now lump sum. Lump sum is done. I mean, now we look at the periodic problems. So first off, notice there's two formulas and they look worse than what we just did. It's probably because of the fraction. There's not a lot more to them, but they're definitely looking more complicated. So the way to tell which one of these formulas to use is to ask ourselves whether the account is growing with each period or shrinking. So an example, growing. Types of accounts that grow every period include savings annuities. So if you're saving with like $50 a month, retirement accounts during the time you're building them up. These are examples of accounts that will grow each time a deposit is made. You will likely see the word deposit in the problem. So this formula, I have again introduced parentheses around the exponent. You won't typically see those when you look up the formulas. Actually, I can do it this way. Let me look up. I'm just looking up compounding formula. So this is our previous formula, just so you can see it's the same stuff, but the NT is not in parentheses. And so this will never work out right.
Okay.
I look at other images. There it is. The NT is not in parentheses. So you're just not going to have the parentheses around it. And it's so important for you to add them. Now here, someone's nice to you and they have parentheses around it. Sweet, that's nice. All right, so same thing here, parenthesis around the exponent, our other formula, parenthesis around the exponent. Critical for your calculator to work out right. So the different thing in here, first off, D. D stands for the periodic deposit, if it's a growing problem. You can remember this formula. The exponent here is positive, it's NT, positive growth, whereas the one that's shrinking is negative NT, and that'll give you decay, it'll shrink. So the easiest way to remember which formula you're using is in the exponent. Is it a positive exponent, that's the growth problems, or is it a negative exponent, which is the decay problem? Now the value of N is determined by how frequently the deposit is made. So if they say you deposit, $50 each month, you're going to use N equals 12. For simplicity, we assume that the compounding frequency matches the deposit frequency. So if we wanted to deposit monthly, but the compounding was daily, the formula would be much more complicated than this. So we make an assumption that the compounding matches how often we deposit. In this class, not necessarily in the world. Okay, shrinking. Types of accounts that shrink every period include car loans, mortgages, and the retirement accounts during the time you were living off of them, which is called a payout annuity. So the retirement account as you're building them is often called a savings annuity. And the retirement account that you're living off of is a payout annuity. Usually you see the word payment, that would be for the car loans and mortgages, or withdrawal, that would be for the retirement account. And you might think payments and withdrawals cause a negative impact on the account, it goes down, that's the negative exponent. Okay. So as an example, you can afford a $600 monthly payment. So the fact that it says monthly payment, we know this is not a lump sum because this is done every month. The company is offering 3% interest rate for 48 months, in parentheses, 4 years. So that's nice because we know time is always in years. So they gave us 48 months, but then did a step for us to get it to years. That's nice. How big of a car loan can you afford? So in this problem, we recognize that it's periodic. It says payment. Basically, when we first get a car loan, the amount in the loan, which looks in this case to be about $27,000, is the initial amount. And then every month that we pay $600 off, that value is going to go down until finally we pay it off. So this is a shrinking formula situation. So we know which formula to use, this one. So we need to know D, we're given the 600. We know R, the interest rate, and since it says monthly payment, we'll use 12, and T is 4 years. This is just a plug it all in and see what happens.
So you don't need the 2 parentheses around, like the 1 minus.
This set, yes.
Oh, you do. Okay.
Yeah, so I've added the exponent parentheses. I haven't removed or changed anything else in the formula. Oops, not that one. So now for the calculator. This is where it'll make or break you. I'm going to go from left to right, top to bottom, and just fill this out exactly as you see it. So 600, left parenthesis, 1 minus another left parenthesis, 1 plus 0.03 divided by 12. Now we have a right parenthesis, then an exponent. You could do this in your head to get negative 48 and not use these parentheses, but I'm just going to let the calculator do everything. Negative 12. You have to use this negative sign, not a subtraction, or else it'll give you errors. 12 times 4. Now, there's a right parenthesis and another right parenthesis. So this is a double close parenthesis set. The double close is another way people remember the formula. You want your car loan or mortgage for a house to close. And so this is the one with the double close parentheses.
The other one
Now,
doesn't have a double close.
It has a double open
Oh, okay.
right there. And you want to open up savings accounts and retirement accounts as a double open. Okay, so we are to the divide. So we divide. And then again, a left parenthesis, 0.03 divided by 12, and a right parenthesis. It is just very careful from left to right, top to bottom. And now for the notes, I computed some stuff to give students like pieces of this, but essentially in one step, you can just do it all. Again, this is the hardest part of this whole thing, getting the calculator to work out right.
Perfect.
Do you have an answer button on your calculator?
No, just enter. Oh, yeah, I do.
You do? So there's one way that you can speed this up a little bit. The 0.03 divided by 12 is used twice. So if you hit enter to begin this problem, Now you can, instead of doing the parentheses and the 0.03 divided by 12, you can just use the answer button. So this would be 600 left parenthesis 1 minus the left parenthesis 1 plus answer button, right parenthesis exponent, left parenthesis negative 12 times 4, right parenthesis divided by answer button. I mean, it's not a lot easier, but if you look at the keystrokes, it
Yeah.
saved a bit.
Okay. Cool.
One nice speed up that you can use. And then rounding to the nearest cent. Even if they don't ask you to, since we're dealing with money, we don't have a 600 thousandths of a dollar currency, so you have to round to the nearest penny. Okay. This next example is a nice example to cover. Because when we're done with the problem, setting it up, what we're trying to solve for is actually the D, and it's not isolated. We end up with D equals, but I'll show you some nice ways to do this problem. Okay, so first off, the analysis. Suppose you want to have 700,000 for retirement in 30 years. Okay, great. Your account earns interest. How much would you need to deposit each month? There are the key words. First off, each month. This is the periodic type of investment. So we have lump sum and periodic. Lump sum are the easier formulas. It's either simple or compound interest. Periodic are these harder formulas. So we're looking at one of the harder periodic formulas, and it says deposit. This is a growth formula. So going back to the growth formula, this is growth. This is the one with the positive exponent. So this is the formula we're going to be working with. Now, if you start with the wrong formula, most of the teachers I know don't give you any credit. So you have to go through this analysis carefully to begin with. Is it lump sum or periodic first? And then if it's periodic, is it growth or shrinking? If it's lump sum, is it compound or simple? Okay, so it does say each month, so we're going to work with n equals 12. And now we have R, simple. We have T, but then we have this 700,000. And there's A or D. Those are the only letters that use actual money in them. The R uses percent rate, so decimal. The T uses years. The N uses how many times a year. A and D are both the ones that can accept dollar values. So this $700,000 is going in A or D. And students often miss up which one it is. Clearly not D. Wouldn't it be nice to deposit $700,000 into an account every month? That's what I'm talking about.
Yeah.
Oh, that would be so nice. Clearly not D. So just ask yourself, could I do this on a monthly basis? Yeah, no, probably not.
Yeah.
So that is A. So we plug that in for A. And we get all this stuff, just plug stuff in. Again, notice the parenthesis around the exponent. And if you compute the stuff inside the parentheses in the numerator, you'll get this number and detail all the decimals you can. The denominator, detail all the decimals you can. And then to solve for D, we need to multiply by the denominator and divide by the stuff in the numerator. So these on the other side basically are just reciprocated. And then you can calculate it. It works out pretty straightforward. So now for the ways to speed the analysis up with our calculators. the answer button's going to play dividends again. Let's work out the 0.04 divided by 12 first. We can see that's the number. Now that that's in there, we can work the right side out. So I'm going to work out all of this stuff right here. It's going to be D in there still. So it's double open parentheses, 1 plus answer button, right parenthesis, exponent, left parenthesis, 12 times 30. This is the growing one, so it should be the one with the positive exponent. Then minus 1, and close parenthesis, and divided by answer. Now the 694.049444, that would be if you divided the 2.3-ish number divided by the 0.003-ish number. That's what this would be. This is also the new number in the answer button position. So we basically have D times this equals 700,000. So to solve, we need to do the 700,000 divided by this stuff, which is now in the answer button. And then this way we can keep ourselves from having to write down all these numbers and still get full precision with our answer. So you have two choices. One is to work out chunks of this and don't lose, don't round, don't miss any information. And then just type it in carefully to get your answer. And the other choice is to use your calculator to work all of it out and then store it somehow, or some other method of not losing the information. I mean, you could still go back to this writing stuff down and have this 700,000 equals D parenthesis that number, the 694.049444, full precision, and then divide by it, get your answer. Again, this is rounded to the nearest penny, even if the instructions don't ask for it. In this case, they don't ask for it. Commonly, money problems just assume that you know to round to the nearest cent.
Perfect.
And you're getting these correctly on your calculator?
Yeah, yep.
Oh,
I'm-
that's so nice. Excellent.
Yes.
Okay, some of the follow-up questions that might be asked. So for example, on our loan problem, whoa. There, thank you. For the loan problem, the car loan, they might ask, how much total did you spend on this car? So knowing that we had $600 a month, if I multiply by 12, that'll be how much a year I spent on the car. And I did this for 4 years. I spent $28,800. But I only bought a $27,107 car. So if I subtract how much I paid, how much I borrowed, I can see how much interest I gave the bank for the privilege of them giving the money up for the month for the car. So this is a common follow-up question. How much interest did you pay to the bank? Or how much did you pay off on the car? Or how much total did you pay? So these types of questions, we have some simple formulas or just some common sense, which is what I just did to figure it out. or the house problem. So we want to have, oh, this is a retirement, the mortgage over here, which we didn't even do yet. But you can afford a $1,200 monthly mortgage payment. How big of a home can you afford? You could figure out how much you spend and subtract how much you borrowed and see how much you paid to the bank. Okay, so the total of all the transactions, whether it's the combined all of your payments or all of your withdrawals or all your deposits, is just D times N times T. That's what we did here. D, $600 times N, how many times a year? 12, and then times T, 4. That's how we figured out how much total money we spent on the car. If it's the total interest earned, the total interest earned will be how much is in the account at the end, A, minus how much we put into the account. Now, if we're earning interest, the larger value will be the final value, the A. Whereas if it's the total interest paid, then like in our car problem, the bigger number is how much we paid. The DNT is bigger, and then we subtract the smaller from the bigger. So this one is DNT minus A, where A is how much you borrowed from the bank originally. And then if it's just a lump sum, it's just the final value minus the initial value to get the interest. So as an example, we deposit $4,000 each year into an account. Deposit each year growth formula. How much will you have in the account in 30 years? How much interest will you earn over those 30 years? So now we have this follow-up question. Well, we solved the first question the same way we have before, figuring out the correct formula. Now this says each year, so we're using N equals 1.
Mhm.
And interest rate and time, and then plug it all in and calculator and get some number. Maybe put a comma in there. $453,132.84. That's how much would be in the account after 30 years. Well, if we want to figure out how much interest, the total interest would be A minus DNT. And so we have the final value minus 4,000 times once a year times 30. And we see that most of the money in the account was given to us by the bank in interest. We only put $120,000 into this account. But at the end of 30 years, we have an extra $333,000. This is where we start to understand somebody asked, man, I cannot think of his name. That's so funny, E equals MC squared. Albert Einstein. Somebody asked Albert Einstein if he could teach only one thing to his kids, what would it be? And he said, of all the things he could have said, general and special relativity and everything equals MC squared, he said the power of compounding. Because if you have compounding working for you, you can put a smaller amount in and end up with a much larger value because the interest is working for you. Whereas if you borrowed a car, we didn't spend a bunch of money on interest, but that was all extra. That's like 2, almost 3 extra months paying off of this car. Now, this is a car loan for 4 years. For a house, it's common for a 30-year loan for you to end up paying almost twice as much as the house was originally purchased for. So much money goes to interest. And if that interest is a loan problem, then you're paying that extra interest. If it's a savings problem, you're earning that extra interest. Okay, and then finally, paying a down payment on a loan. So sometimes they'll talk about, like this one, you want to buy a home, you plan to pay 5% as a down payment and take out the 30-year loan for the rest. How much is the loan amount going to be? Now, this isn't usually the only question. It's usually what will the monthly deposit or monthly payment be? But in order to work out like the monthly payment formula, way back up here, way back here, negative monthly payment, you need to know, you either need to know D or you need to know A. So, how much are we going to borrow? So we work out the down payment. It's the percent times the cost, 5% in decimal form times how much it costs. And we get $10,450. That's how much we're going to pay in a down payment. So the loan amount A would be the difference. Subtract that from how much we want for the house, and that's how much we have to borrow.
Okay.
Now we could also work this out in one step. Basically, if we pay off 5%, we still have 95% left over.
Hmm. Okay. So what are those equations going to be on the test, or we just need to know those two?
These last few, no, they're not on the test.
Okay.
Yep. I give them here just so that that makes it easier to work with, but you want to just kind of
No.
get this into common sense.
Okay.
Yep. All right, so we now have some time that we can work through a selection of the problems on the right. So this is up to you. Would you like to do simple interest, a compound
Probably
interest?
the last few ones. I
Okay.
feel like those ones seem harder.
Okay, well, let's work our way backwards, 6, 5, 4, 3, see how far we can get in the next 18 minutes. Okay, well, let's work this out. So we want to pay a 20% down payment. So we can find the down payment. By working out 20% of how much the house is for. Or if we pay down 20%, how much is left? What do we still owe?
80.
So this would be the one-step approach. So either way, let's see what we get here. So 0.2 times 255,000. So this is the amount of the down payment. If they ask how much are you paying, you just have to work out the actual down payment. And then how much you're going to borrow from the bank will be the full value minus the down payment you're making. That should be, I think it's 204,000. Let's double check by doing it this way as well. Yep, perfect. One way or the other, this is how you would compute how much money you need to use the A value in your, this would be a shrink down loan amount, loan formula, the negative exponent formula. This is how you work out the A. Questions?
I don't think so. So we don't need like all of the information in the word problem, like the 30-year
So
and all that.
So it was way late last night when I was finishing this up, and I was like, let me just show them this one little piece. Yes, so the final thing that we need to plug this stuff in. If we wanted to like find the payment. This is a double close. 1 plus 0.0. Oh, so we don't even have the interest rate on this one.
Mhm.
I'm assuming it's monthly payments for 30 years. We don't know R, but this is where we would go. They would provide you with the interest rate. And then you could work out and solve for D. So this is not usually the only question. So if I were to go and pull up like an annuities question from the homework,
Mhm.
looking for a down payment problem. There we go. So you want to buy a home, you plan on paying % down and take out a 30-year loan. How much is the loan amount going to be? So that's what we just saw how to do. What will your monthly payment be? And here they provide us the interest rate, because that's what we were missing. So it's a multi-step question.
Okay.
Yep.
Perfect.
Yep. Okay. We want to buy a $151,000 home. Found a bank that offers a 30-year loan at 5.5% interest. What will your monthly payment? What will be your monthly payment? And how much would you end up paying the bank for the home after 30 years? You don't just pay them the $151,000. No. All right, so monthly payment right there. Monthly, this is periodic, so it's one of our ugly formulas. And payment, this is the shrinking problem. Payment or withdraw are the keywords for the shrinking problems. So I'm not looking at the correct formula over here. It's the other formula with the negative exponent.
Oh, okay.
So it's this formula, the negative exponent.
Okay.
I have them memorized, kind of sad, but true. So this value, could you afford that monthly? I wish.
Yeah. No.
That's going to be the A value. D times 1 minus, parenthesis, 1 plus 0.055 interest rate over, we're doing monthly payment, so N is 12, parenthesis, negative 12 times 30, double close. We want this thing to close. We have our house paid off. Denominator is the R over N.
So we just plug that in, right? From left to right.
Yep. And let's do the simplifications as much as we can. So since that's in there twice, if we store it in the answer button, and that's an ugly looking number, wouldn't want to write that down. Now we can work out the right side. Left parenthesis, 1 minus. Left parenthesis, 1 plus answer button. Right parenthesis, exponent. Left parenthesis, the negative, 12 times 30. Double close, right, and divide by answer.
So my
Yes.
the double close, do I need to make sure it's not a double close on the exponent? Like go down for some reason. it's
Oh,
not.
so if you have that type, yes.
Yeah.
Yeah. In fact, you probably don't need the parentheses around the exponent for your calculator because you know you're up in the exponent. Yeah, the math print allows you to have this correct without all the parentheses. You should get 176-ish. Is that what you got?
Yes.
So if you wanted to show some work here, you'd want to write the whole bit of information. I'm going to move this off screen so I don't lose it. 1, 2, 1, 7, 6, 3, 1. All of that. And then we can solve for D. You can see you just need to divide by that number into the 151,000. And since we have the answer button storing that 176, we can just do 151,000 divided by answer button without having to type that whole thing in. 857.36.
Perfect. That's what I got.
Excellent. Now, the next question. So let's put a box around this. This is the monthly payment. We could even label it monthly payment. Make sure we get full credit. How much would you end up paying the bank for the home after 30 years? So that's just the total payment. So in our formulas, that's the total of the transactions, the total payments. That's a DNT. So DNT would be, we're paying $857.36, 12 times a year for 30 years. Don't use the answer button this time, because the answer button actually holds a bunch of extra microcents that aren't reality. We can't make this what's on the calculator. We can't make that monthly payment. So we actually have to round because of reality. That number times 12 times 30. This is the total amount of our payments.
Okay.
308,649.60. That's the total payment. Now, if they ask for the interest, we would take the total payment and subtract the original cost of the house. This is how much we actually gave the bank for the privilege of using their money to buy this house. That's the scary one. We spent more in interest than the house was worth. Well, a lot of wealthy people have the habit of not buying anything that's shrinking in value with credit. Buy it with cash. If you can't afford it, get a cheaper house. Houses are a little bit different. So what I've done, the two houses that I purchased both had mother-in-law apartments. And so I had somebody else paying me rent that paid paid all of the interest plus some of the mortgage. And that's how I managed to be able to buy a house and be able to afford it. And some people buy really nice houses, and that's where all their money goes, which sucks, especially this last go around. Houses got so expensive.
So much.
Yep. So work out the DNT. It's pretty straightforward. And then look at that number and compare it to the other number in the problem, in this case, it's a house, and you'll see which one's bigger, so you'll know which way to subtract to find the interest. If you subtract it the wrong way, you'll get a negative number, which is
Mhm.
obviously not interest.
Mhm.
Yeah, great.
Perfect. Yeah, I think
So-
I'm good with the other ones.
Okay. So let's just look for keywords in this problem.
Okay.
Deposit. Each month. Each month, this is periodic. Deposit, this is the growth formula.
Okay.
Deposit. Each year. Periodic growth formula. Invested. Now it says per year, but that's part of the interest statement. That's R. That whole thing is R. So this $50,000 is invested. It doesn't say it's invested more than once. This is lump sum. Compounded. If it says compounded, it's lump sum. That's the key word for the lump sum problems, either compounded or simple interest. Compounded, lump sum problem, easier formula. Interest, how much interest will be earned? That's a compounded, quarterly, lump sum problem. Now for the lump
The
sum
shrinking
problem,
one, right?
no. So the shrinking, growing are all of the periodic problems.
Oh, okay.
The lump sum are either simple interest or this compound interest.
Okay.
Perfect. Okay, 500,000 saved for retirement. You might think savings, that's awesome. This is a growth problem. Nope, withdrawal. Each month. Each month, this is a periodic, so it's a shrink or grow. Withdrawal, this is a shrink problem. You know which formula to use. You want to buy a car, buying a car, payments, and monthly. This is periodic, and
Grow.
oh, I wish. No, payment is a shrinking problem.
Okay.
So basically the account value will be 15,000. After the first month, it'll be 14,800 and then 14,650. It's going to continue to go down until it's finally at zero when you
Yeah.
paid off your car. So this is a shrinking problem. Yep, payment, shrinking problem. Payment, oh, down payment. And then monthly payment, shrinking problem. Monthly payment, shrinking problem. Monthly deposit, growth problem. This one does say compounded monthly. But then it's after they made payments. So that's plural. So this is not a lump sum because it's more than one payment. There's actually a really interesting problem because you end up running the formula twice. There's two different stages of this. You pay it down for 10 years. And then they want to refinance. And then what's the balance after 7 years of the refinance? That's a hard question, actually. But that, it's 11 o'clock. That's the time that I have for you. I hope this has been beneficial for you.
Perfect. Thank you so much. I really
Yeah,
appreciate
I'm so glad someone showed today. Thank you. For making this feel like it was worth it.
it. Yes, it was great. Thank you so much. I appreciate it.
Yes, you're welcome. Hope you have a wonderful day.
You too.
Okay, bye.